talk about a topic called rigid body mechanics. Rigid body mechanics is the area of physics that studies how an object rotates and moves around an axis of rotation when it has an unbalanced torque acting on it. If you remember, previously we learned that torque is a force that acts at a distance from the center of mass of the object, causing it to rotate about an axis of rotation. Now, if there is an unbalanced torque, we're going to have an angular acceleration in the object. So that leads us to describe a new set of variables, very similar to the ones that we have been using for linear motion, but talking about rotational motion instead. So first we have S, which used to be our displacement, which is going to be converted into theta, which is now called the angular displacement, and it's measured in radians. If we want to convert from the displacement to the angular displacement, we just multiply the angular displacement by r, which is the radius of the rotation of the object. Then we have u, which used to be our initial velocity, which we will convert into initial angular velocity, which is omega I in radians per second. Our final velocity v will become our final angular velocity omega f, also in radians per second. To convert linear velocity into angular velocity, we also multiply by r. Then we have the acceleration, which becomes the angular acceleration alpha. The units for alpha are radians per second squared. Same thing, if we want to convert from the angular acceleration, we multiply it by the radius and it gives us the linear acceleration. Time does not change. Time is the same either in linear motion and in rotational motion, so we don't have to convert anything there and we still use seconds. And mass is converted into something called the moment of inertia. So I'm going to stop there for a second and talk about the moment of inertia. It's how much an object resists rotation, just like mass is how much an object resists linear motion. So moment of inertia depends on two things: how much mass there is and how it is distributed around the center of rotation. It also depends on where you choose the axis of rotation of the object. Because if you want to rotate something like this, it's going to be different than if you want to rotate it like this, if it's the same object. So in moment of inertia, we can think about the same mass but distributed in a different way, having an effect on the rotation and the velocity of rotation of the object. So I drew here two skaters that you've seen maybe in ice skating shows. You know, they go around and around. Well, what they do is they go around with their arms outside, so their mass is far from their center of rotation, which is their body. They go around and then they pull in their arms and their legs and they start rotating much faster. Because when they contract all that mass into a smaller area, they decrease their moment of inertia, generating much more speed. So the moment of inertia, if we have that separate masses, for example, 4 tennis balls connected by strings, we're going to pick our axis of rotation, and our moment of inertia is going to be the sum of each mass times its distance to the axis of rotation squared. So we can do some exercises to practice that, but it's basically knowing that the farther away the mass is from the axis of rotation, the harder it is for it to rotate as quickly. So now we can go back to our big list of equations. You know the equations for suvat, for linear velocity. They will all be converted exactly the same way, but using the rotational variable instead of the linear variable. So for example, we have displacement equals initial velocity plus final velocity over 2 times time. Now we're going to have our angular displacement equals a final angular velocity plus initial angular velocity divided by 2 times time. Same thing with this one to get the final angular velocity, this one for displacement with an acceleration, an angular acceleration, and this one for the final angular velocity. We have to take into account, just like in linear motion, these equations work for constant linear acceleration. In rigid body mechanics, these equations work for a constant angular acceleration. That means that there has to be a torque. Newton's second law also has its equivalent equation. Instead of force equals mass times acceleration, now we have torque equals moment of inertia times angular acceleration. That leads us to a new equation for momentum. Momentum was mass times velocity. Now we have angular momentum equals moment of inertia times our angular velocity. And if you remember before, if there was no resultant force acting on an object, momentum was conserved. Well, now the same thing happens with rotation. If there is no resultant torque acting on an object, the angular momentum is conserved and constant. So that's going to have many interesting effects, like in galaxies and the speed of planets, that will be interesting to look at. Almost done. Now we have impulse. Impulse or change in momentum used to be force times time. So now we have our angular impulse or change in angular momentum, which is torque times time. And our kinetic energy had two versions, 1/2 mv squared and momentum squared over 2m. And now our rotational kinetic energy is going to be 1/2 I omega, which is moment of inertia times angular speed squared, or angular momentum squared over 2 times moment of inertia. So these equations will all be useful. This one specifically, there might be examples in which there is both rotation and linear displacement, such as a ball rolling downhill without slipping. In that case, you're going to have to use both equations because it's both having a linear speed and an angular speed. So I hope this is clear, and we will do some examples next time.